Welcome back. So when we discussed the root locus, we said that a point in the complex plane is on the root locus if the angular contribution from the poles and zeros to that point sum up to an odd multiple of 180 degrees. Okay, now that suggests that maybe we'll have to scan through the entire complex plane looking for points and then plugging them in and evaluating the angle to check whether they satisfy the condition in order to detect all the points on the root locus. But that is not going to be possible or feasible. So what we do is that we learn some principles, and these principles then help us to sketch the root locus without having to test for each point to see whether it satisfies the condition. Of course, the principles are derived from the same condition that we stated above. Then the second aspect of it is, once you're able to sketch the root locus, we can now apply some more principles to define some particular or peculiar or specific points on the root locus to help us to draw it or plot it to some level of accuracy. Okay, and then we can even proceed to calibrate the root locus. So today we are going to start with the principles that help us to sketch the root locus. So we're going to start with sketching the root locus. Okay, so we are going to first learn 5 fundamental principles that help us to draw a basic sketch of the root locus. The first principle is that the number of branches. Okay, now this states that the number of branches of the root locus equals the number of poles of the closed loop system. Okay, and this assumes that poles can be both finite and infinite. So here, when we talk about the number of poles, we are talking about the number of finite poles plus the number of infinite poles. Okay, or you are saying the number of finite poles plus the number of poles at infinity. Now this stems from the fact that for a given system, okay, the total number of finite plus infinite poles, okay, for the closed loop system equals the total number of finite plus infinite zeros. Okay. So when we take this system, what we are saying is that for the given system, the total number of finite plus infinite poles equals the total number of finite plus infinite zeros. So what this suggests is, if I have a system like this, for example, T of S equals K gh of s equals let's say s squared over into s plus 1, so I can attach k to it, into s plus 2 all over s plus 4. Then here the finite poles will be equal to 1, that is at -4, and the finite zeros will be equal to 4, that is at 0, 0, -1, and 2. Okay, so what this suggests to me, or what this says, is that the total number of poles at infinity will then be equal to what? Well, it's going to be equal to 4 minus 1 equals 3. In similar fashion, the total number of poles, if I had a system such that kgh of s equals ks into s plus 4 all over s plus 1, s plus 2, s plus 3, s plus 5. Then here you see that your finite poles equals 4, and finite zeros equals 2, implies the infinite, or the poles at infinity, will be equal to 4 minus 2, which is 2. So the idea is that, and later we'll derive it, that the closed loop poles will actually, if you have a system where the polynomial in the denominator has a power greater than the polynomial in the numerator, then you are going to have the poles moving and ending in infinity. And if the polynomial in the numerator is greater than the polynomial in the denominator, then you are going to have the poles some poles starting from infinity. So that will be covered in the subsequent lectures. Okay. So whatever system you have, the number of branches equals the number of poles, and that makes perfect sense because it is the root locus is actually the path that is traced by the poles. And so if there are 7 poles, then you, in the closed loop transfer function, then you expect 7 branches. Okay, and what we are saying is that if you take the open loop system, the number of poles of the if you take the open loop transfer function, the number of poles of the closed loop transfer function, okay, is going to be equal to either the number of poles of the open loop transfer function or the number of pole zeros of the open loop transfer function, whichever is greater. So let me state that. So it means that the number of branches of the root locus equals the number of poles of the open loop transfer function, or the number of zeros of the open loop transfer function whichever is greater. Okay, so that is basically, and I think you can easily derive this from the expression we came up with earlier. Okay. The second principle we will study is the principle of symmetry. And when we start sketching, we will see that, okay, the root locus is symmetrical about the real axis. Okay. In other words, if we have complex poles, they occur in complex conjugate pairs. So if you have complex poles, they will occur in complex conjugate pairs, and that is what we have studied earlier, because the systems we are dealing with, the linear time invariant systems, have the transfer function with the characteristic equation having all the coefficients being real, and the only condition under which the coefficients will all be real is if one, the poles are real, or two, the poles are complex conjugates. If you have any complex pole in there which is not a complex conjugate, then you are going to have some complex or imaginary coefficients for the characteristic equation, which is not the case with the systems that we are dealing with. Okay. The third principle, so whenever you plot your root locus, ensure that it's symmetrical. It's either it's lying on the real axis, or if it projects into the complex plane, okay, then that portion above the portion above the real axis, okay, the portion above the real axis should be the same as the portion below the real axis. If you don't get that, you know that you are wrong. Okay. The number 3 principle, okay, talks about the location on the real axis. Okay, so this talks about the location of the root locus on the real axis for k greater than 0. Okay, so for k greater than 0, where would the root locus be located? Okay, and here we say that for k greater than 0, okay, the root locus exists to the left of an odd number of real axis, okay, real axis, finite, open loop, okay, poles, and or real axis, finite, open loop, zeros. Okay, so what this means is that if I have a system with, for example, these zeros and poles, okay, let's say there's a 0 here, a 0 here, a pole here, a 0 here, a pole here, a pole here, a 0 here, a pole here, a 0 here, pole, 0, pole. Okay, so these are a number of poles. I'm just going to number them. Okay, so let's say this is 1, 2, 3, sorry, 1, 2, I mean, put the numbers with different color just so we know. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I have 12. So the number of zeros 6, the number of poles 6. Okay. Now I want to find where the root locus will lie in the real axis. So first, I'm going to look for the odd numbers. So the first odd number is going to be this. Then the side here, there will be root locus lying to the left of that odd number of poles plus zeros. Okay, so this is odd number, only one pole, then only 1 0. Then 2 is even, so it will not be counted. Then 3 is odd, so I will count the left side to that, and there will be another root locus lying on the real axis there. And then 4 is even, so I will not count. 5 is odd, and so I'm going to count to the left. And 6 is even, 7 is odd, okay, 8 is even, 9 is odd. So to the left of an odd number of poles and all zeros. And then 10 is even, 11 is odd, so I'll put that one here. Okay, so this is another rule that you come across. So this means that to the left of every odd number of poles and zeros, there is going to be a root locus lying on the real axis. Okay, so that is another, and this makes sense. Okay, so this makes sense because this stems from the fact that if you look at it critically, for example, if I pick a point here, okay, then the pole here, the zero here, will contribute an angle. Okay, so every zero and or pole at the left of the point on the real axis contribute (0° to the angles. Okay, and every point or every zero or pole at the right of the point on the real axis contribute 180 degrees. Okay, so if I take this point, then if I draw a line from this to that point, then the angle is going to be what? It's going to be 180. Okay, the angle from the positive projection of the real axis, this angle is 180. Okay, now if I draw another point, another from this side, then the angle from the positive projection of the real axis is going to be 0. Okay, so for this point here, x, the angle contribution from the pole here on the right is 180. That on the left, or the 0 on the right, is 180. That of the 0 on the left is going to be what? Is going to be 0. Okay, which means if I have, for example, I pick this point, then because I have two zeros, they are going to contribute 180 plus 180, which is equal to 2 times 180. But we said that if the point will be on the root locus, then it should be an odd multiple, which means if you pick a point here, the angle is going to be 360, and that is wrong. Okay, that's going to be wrong. So if you pick a point here, all the points to the left of that will contribute 0, 0, 0, 0. So we are not interested. But the point to the right will contribute what? This one will contribute 180. This will contribute 180. And that will contribute 180. So we are going to have, actually, it's going to be 360 minus 180 Okay, this is the total angle of zeros minus the total angle of poles, and that is going to be 180. And you see that 180 is 1 times 180, which is an odd multiple of 180. So that is what actually we use to derive that principle.